In this video, I'd like to talk about the proof strategy called indirect proof. This corresponds to section 2.2 in the textbook. Alright, so to begin discussing indirect proof, first we need to talk about some related statements to a conditional or an if-then statement. Now we've already talked about the if-then format, and we've used the letters P and Q to indicate the premises and the conclusion. We've also talked about the converse of the conditional, which is formed by switching the hypothesis and the conclusion. So in symbols, this would look like Q implies P or Q arrow P. And in words, we would switch this and we would write if Q, then P instead of if P, then Q. Alright, so as a review, we can practice this with the following statement. If Tom lives in San Diego, then he lives in California. So the converse, I'm going to write maybe I should do, CONV for converse. The converse would be if Tom lives in California, then he lives in San Diego. Alright, so notice also I've switched the subject Tom and then the pronoun he, just so that it makes a little more sense when you read this. So we did talk about the fact that it's okay to reorder some of the words or change the wording a little bit as long as you've switched the hypothesis and the conclusion. Okay, then there are two more related statements that we haven't talked about yet. The first is the inverse of the conditional, and you form this one by, it's called negating the hypothesis and negating the conclusion. So we use this little tilde or squiggle symbol to indicate the opposite or kind of like not. Right? So we would write, we would read this, if not P, then not Q. Right? Or not P implies not Q. So you're kind of taking the opposite of the hypothesis and the conclusion. So for our statement, the inverse would be if Tom does not live in San Diego, then he does not live in California. And then finally, a fourth statement would be the contrapositive. And this one is sort of a combination of the converse and the inverse. The hypothesis and conclusion have been switched from the original conditional, and both of them have been negated as well. So this would read, if not Q, then not P. So there are two ways that you can form the contrapositive. One of them is by looking at the converse, in which hypothesis and conclusion are already switched, and then all you do there is you negate both of those. Or you can look at the inverse, where they're already negated, and then you can switch them. Okay, so either way you choose to do this, you'll end up with, for this statement, if Tom does not live in California, then he does not live in San Diego. Alright, so let's look at these four statements and decide which of them are true and which of them are false. So there's no set rule about whether a conditional is true or false. It does depend on the statement, and the same thing applies for these other three related statements. But in this specific situation, right, if Tom lives in San Diego, then he lives in California. That is a true statement. Okay. The converse, if he lives in California, then he lives in San Diego. That's false. So there are other options. He could live in Los Angeles, and that's still in California without being in San Diego. The inverse, if he does not live in San Diego, then he does not live in California. Well, that's false. So for example, if he lives in Los Angeles, that's not living in San Diego, but it's still living in California. And then the contrapositive, if Tom does not live in California, then he does not live in San Diego. So if he's outside of the state, then he's not in that city. Okay, that makes sense. That's true. Right. So notice in this case, the conditional and contrapositive happen to both be true, and the converse and inverse happen to both be false. So this happens in general. The conditional and contrapositive will always agree with each other as far as true or false goes. So they either both have to be true or both false. And then similarly, the converse and inverse also both have to be true or both false. Okay, now you could end up with all 4 statements true or all 4 statements false, but you would never have a situation where the converse is true and the inverse is false, and you would never have a situation where the conditional is true and the contrapositive is false, or something like that. All right, so because of that, this sort of leads us to the indirect proof strategy. Since proving a conditional, since a conditional and contrapositive are either both true or both false, then proving a conditional is the same thing as proving the contrapositive. So like if I can prove this one, then I would also know that the conditional is true. So even though we state statements as conditionals often, sometimes it's easier to look at the contrapositive when trying to do a proof. So the ones we've done so far have been called direct proofs, and the format for those has been we have a statement like if P then Q, and then we've started with our hypothesis, P, the given, all of that information, and then we've tried to reason through theorems and postulates and definitions to show that Q is true, and then that statement is proven. So here's what an indirect proof looks like, and this is often called the law of negative inference. You don't need to memorize that, or the law of contraposition. It's called an indirect proof, proof by contrapositive, or even proof by contradiction. So this is just another form of deductively proving something. And remember that deductive means starting with assumed or known information and then logically reasoning to other information that must be true. All right, so here's how this works. We start with a statement like if P then Q, and then we assume that Q is not true, and then because if we can show that not P follows from that, right, then what we've just shown is that basically this part is proving that the statement or starting with the hypothesis if not Q definitely must lead us to the conclusion not P. And then if we can prove that, then we also know that the contrapositive of that, or the original conditional, if P then Q, is also true. So here's an example. And then let's just try to form the conclusion to this argument. So let's say that we know, we're going to start with this statement. If I am in TLC 509, then I am on the campus of LBC. Okay, I am not on the campus of LBC, therefore, what can you conclude? Right, so if we take I am in TLC 509 as P, and I am on the campus of LBC as Q, right, then I am not on the campus of LBC is not Q, and therefore that means we can conclude not P, or we can conclude I am not in TLC 509. Alright, so we've started with some examples that you can sort of verify using common sense or common knowledge. Alright, so just think through this argument and make sure that you agree with this. Okay, to make sure that the first statement is true, and then see if you can see why, if I am not on the campus of LBC, why that absolutely must mean that I am not in TLC 509. Alright, so we're going to start out with just reading through an example of an indirect proof, and then we'll talk a little bit more in detail about the structure of one of these and how you go about putting one together. Alright, so this is example 2 from the textbook, and here is the given statement. In figure 2.12, ray BA is not perpendicular to BD, and we are supposed to prove that angles 1 and 2 are not complementary. Right? So this is a more specific given. We're not looking at the general statement, but if we take this as our premise or our hypothesis P, and then here's the Q that we're trying to get to, okay, then an indirect proof means you start by assuming not Q, and then you try to show not P. All right, so let's look at the diagram first of all and just sort of use intuition to try to see why this might be true. All right, so BA and BD are not perpendicular. Okay, so these rays are not perpendicular. All right, and there would be some technical details to go through, but basically we can show that this is not a right angle. Right, so since that's not 90 degrees, then 1 and 2 don't add up to 90 degrees. They would add up to something different, and then that would make them not complementary. Okay, so a direct proof would mean just starting with the fact that these are not perpendicular and then trying to show that 1 and 2 are not complementary. Now, if you start with the fact that they're not perpendicular, that doesn't give us much to work with because we don't have any theorems about rays that are not perpendicular. We don't have any, any definitions or postulates or really anything to work with. So it would be pretty hard to do this directly. However, if we try to go about this indirectly and assume not Q, okay, let's take a look at what not Q is. Well, Q is that 1 and 2 are not complementary. So let's say we start by assuming that they are complementary. Well, then we have some stuff to work with because we know the definition of complementary. We know that that means that the angles add up to 90. And then we can work from there to talk about 90-degree angles and right angles and then perpendicular lines and things like that. All right, so let's read through this and see if the reasoning sort of makes sense. See if it's logical. So suppose that angles 1 and 2 are complementary, then that means that their measures add up to 90 degrees because the sum of the measures of two complementary angles is 90 degrees. We also know that the measure of angle 1 plus the measure of angle 2 is the measure of angle ABD by the angle addition postulate. Okay. In turn, the measure of angle ABD must equal 90 by substitution. So we said that 1 plus 2 was 90 and 1 plus 2 was ABD. So then these two things, by substitution, those are equal. All right, so this angle ABD is a 90-degree angle, and then that means, by definition, that it's a right angle, and then we have a definition, or I think a theorem in this case, that says that if that's a right angle, then those two rays must be perpendicular. Okay, so this contradicts the given hypothesis. Right, so what we're trying to do here is just start with assuming that our conclusion isn't true, and then we're going to try to get to the point where we show that that would mean that the thing we started with is not true. All right? But then we know that this was true, so in other words, there's a hole in our reasoning. Right? So if you look at all of the statements we've made, okay, all of these were justified. The only one that wasn't justified was this one, assuming that Q is false. Right? So if you can justify everything, but you get to a contradiction of this hypothesis, which we know to be true, or we're assuming that, okay, then this thing that was unjustified is the gap or the weak link in the reasoning. So this tells us that this supposition that we started with is false, okay? So that would mean that 1 and 2 are not complementary, and then that's what we were trying to prove. Okay, so in general, here's our strategy for an indirect proof. Okay, if you want to prove that P implies Q, then you start by assuming that not Q is true. And of course we know that this is going to turn out to be a weak link and that, not Q. We actually want it to be false, but we're going to assume that it's true and then try to show that that's not possible. Right? So we will start with that assumption and then continue using definitions, postulates, theorems as we've done before, and then hopefully we get to a contradiction. Right? And if we do, we know that this means that not Q must be false, right? And therefore that Q must be true. Okay? So if not Q is false, then Q is true. All right, so this takes a little bit of getting used to. It's a different way of thinking about these proofs. So I did want to look at another example before we try to jump into writing one of these on our own. So here's example 3 from the book. And we're trying to prove the theorem if two lines are cut by a transversal so that corresponding angles are not congruent, then the two lines are not parallel. Okay, so I've copied the figure 2.13, and to just make this specific, we start as usual with trying to label the diagram and in the given discuss specifically from the diagram what we have assumed in the hypothesis. Right, so we're starting with if two lines are cut by a transversal so that corresponding angles are not congruent. Right, so here are our two lines, L and M, cut by transversal T, and then we need two corresponding angles that are not congruent. So we just picked out 1 and 5, and we said that they are not congruent. And then what we're trying to prove is that this means the two lines, L and M, are not parallel. Okay? So in addition to assuming this given information, we're going to assume this, but we don't have much to work with from there. Okay? So we don't know anything about lines if the corresponding angles are not congruent. That doesn't tell us anything. The only theorems and postulates we have so far say that if we start with the fact that 1 and 5 are corresponding, or actually if we start by assuming the lines are parallel, then we would know that 1 and 5 are congruent. Okay, that's the only thing we have to work with from the book. So instead of working with what we don't have, hey, we're going to assume the opposite of Q. All right, so here's P. This is Q. We're trying to prove L is not parallel to M. So we're going to assume temporarily that not Q is true, or in other words, that L and M are parallel. Well, now that gives us some stuff to work with. Okay, so when these lines are cut by transversal T, the corresponding angles, including 1 and 5, are congruent. So that is postulate 11 from the book. And there's our contradiction. It was really short to get to, right? So if we start out with that L and M are parallel, then that would mean that 1 and 5 are congruent. Okay? But this contradicts something that we assumed. We assumed that they were not congruent. Right? So we have our contradiction, and then that points the finger at this false assumption. This is the only thing that we didn't justify, and it shows that that's false. Okay? So then that means that the opposite must be true. It must be true that lines L and M are not parallel. All right, the other thing I wanted to point out from these examples, notice we've switched over. We're not doing two-column proofs anymore. These are called paragraph proofs, and we're basically just writing sort of a narrative or working through these statements, still justifying everything, but it's more conversational rather than an ordered list or an outline of a proof. Okay? So you'll see lots more transition words, suppose, then, in turn, therefore, okay, and these are all types of words that we would use in proofs. Thus, since, it follows that, things like that. Okay, so let's try our own indirect proof. This is example 4 from the textbook. Alright, so we are trying to prove, let's see, the given is that in this figure, plane T intersects parallel lines, or I'm sorry, parallel planes P and Q in lines L and M respectively. And we are trying to prove that that means L and M are parallel lines. Okay, so let's see. We don't have any theorems at this point that talk about what we're trying to prove. So instead we're going to use the indirect method, and we're going to start out, and you would either say suppose or assume. And the first thing you write is assume, and then you write the opposite of whatever the proof statement is. So assume that L is not parallel to M. Okay? And you'll notice in these we use sort of a combination of symbolic shorthand like this and then full sentences. So you can write it out in words if you prefer to see it more formal. Okay, so I would actually write L is not parallel to M, or you can do a sort of a combination with some of these symbols thrown in. Okay, so once we've made this assumption, now informally, if you're trying to figure out where to go from here, you could do one of two things. You could think about what we know about lines that are not parallel. Okay, so picture that in your head. All right, here's what I'm picturing. All right, two lines intersecting. Or you can try to see from the diagram what's the problem with this statement. Why does this need to be, why does this turn out to be false? Right. So let's say that L and M are not parallel. Okay, then I'm going to kind of draw them intersecting here. And they actually are parallel, so I need to, fiddle with this a bit to get them to look not parallel. Okay, so let's say they intersect kind of like this. Okay, well, what's wrong with that? Well, look at the given information. Let's see if we can find, just sort of informally, any contradictions. So T is intersecting parallel planes P and Q. Okay, so think about parallel planes. If you sort of extend P, well, we know that this line L is in P, right, and M is in Q, and parallel planes never intersect each other, right? So that's what it means for planes to be parallel as well as lines. So if you're going along, line M, which is in plane Q, there should never be a point where it touches plane P. Okay? However, if these lines are not parallel, then we know that there is at least this one point, or exactly this one point, where they do intersect. So that's the problem with this. Okay? And then we basically just need to say that and sort of logically write out what we just said. Okay? So start with the fact that L and M are not parallel. Okay? Then this means L and M intersect at a point. And then we'll often just name whatever it is we're talking about so that we can refer back to it later. So I'm going to say call it A. Okay, and then I can talk about point A instead of referring back to the point where L and M intersect, which is a little bit more wordy. Alright, and so then I need to show that the problem is that point A shouldn't really exist. There shouldn't be a place where P and Q, those two planes, intersect each other. Right? Well, how do I do that? Alright, well, I want to state that since A is on line L, then A is in plane P. Okay? And similarly, since A is on line M, then A is in plane Q. Alright, so there's a point A that is in P and Q, but this contradicts the fact that they are parallel. All right, so since A is in plane P and plane Q, okay, this means planes P and Q intersect at A. Okay, sorry, that's a little hard to see the blue on the black. Okay, planes P and Q intersect at A. And then you want to state that there's a contradiction. Okay, so this contradicts the fact that P and Q are parallel. Okay, so then since we've shown that there's a contradiction, this means, and I'm going to continue the proof up above. So next I would write this means, and then I just want to point out that this assumption I made is faulty. Okay, so this means L is not parallel to M is false, and therefore the opposite must be true, or therefore L must be parallel to M. And then that's the end. Okay. Now here's another little symbol you'll see when you've reached the end of a proof. Sometimes we'll write a little square, either blank like that or you can shade it in. And that just sort of indicates the end of a proof. Alright, let's do another example. And this will be our last one. Okay, so example 5 from the textbook. Prove the statement, the angle bisector of an angle is unique. Okay, so you will see indirect proofs used in several situations. One of them is when you're trying to prove something that has a lot of nots in it. So if not this, then not that. All right, so it's handy to think about the opposite and then work from things that we actually do know. And the other time you'll use this is when we're talking about uniqueness or existence of things. So, how do we prove that there's only one angle bisector? Well, a nice way to prove this is to assume that it's not the only one, that there are two of them, and then that gives you kind of double the information to work with, because then you've got two angle bisectors, and we just have to show that one of them can't exist. Alright, so let's start with, we should probably talk about what this looks like in if-then form. Right? So in if-then form it would be if, here we're talking about array, so if array is an angle bisector of an angle, then it is unique. Okay, so we're trying to prove the uniqueness part. So we've made this more specific in the diagram. In this figure, ray BD bisects angle ABC. So we're assuming this premise, P. We're going to start with that. And then we need to prove that it's unique, that it's the only angle bisector for that angle. So that's Q. Alright, so in indirect proof, you're going to assume P like always, and then we're going to assume the opposite of Q. Right? So we're going to say, to begin, suppose, and then we write the opposite of Q. Okay, so suppose ray BD, let's see, actually, why don't I start with this? Let's be specific from the beginning. So let's suppose that there's another specific ray that is an angle bisector. All right, so I'm going to draw this in. And your textbook calls this one BE. Okay, so I'll do the same. So suppose ray BE is an angle bisector of this angle, of angle ADC. Oh, ABC, sorry. Okay, so think about why this would be a problem. Well, we know that if something is an angle bisector, it's cutting the angle in half, right? So if we put some numbers to this, like let's assume maybe the original angle is, say 60 degrees, okay, angle ABC. Well, that would mean then that ABD is 30, and ABE is also 30. And you can sort of see from the diagram, like it looks like it's smaller, but yet it's still the same measure. All right, so we've got to figure out what would that mean then, all right, for this other portion of the angle, right? And there's no way for this to happen. So in other words, we're going to try to show that you can't have that smaller angle, the new one we made, ABE, that can't also be half of angle ABC. Right? So let's start by assuming everything that follows from an angle bisector, and let's see where we end up. Okay, so suppose BE is an angle bisector of ABC, then this means that the measure of ABD is 1/2 the measure of angle ABC. Okay, and the more advanced we get into these proofs, you'll notice we start to skip some more basic steps. So angle bisector would, technically mean that ABD and DBC are congruent, and then we would show that their measures are the same, and then we would go from there to showing that one of them is half of the larger angle. So we've skipped some of the algebraic steps to get to that point. All right, and then since BE is also an angle bisector, it is also an angle bisector of angle ABC, then the measure of angle ABE is also 1/2 the measure of angle ABC. Okay, so the problem here is that, well, one thing we know is that the measure of ABE plus the measure of EBD equals the measure of ABD. Okay, and how do we know that? So we do want to justify when possible, all right, especially if it's not just a definition. So you'll notice, previously we sort of skipped, it almost looks like we skipped a reason, but by saying then, it means that we had the justification before we stated what we were about to say. Okay, so it's the fact that BE is an angle bisector that implies this 1/2 the measure of the angle type statement. Okay, and then since it's an angle bisector, then this, so we're basically relating it back to the definition of angle bisector as our reason. We don't have a reason yet for this equation, so we do need to state that. Right, and the reason is by the angle addition postulate. All right. Okay, so now what can we do with this? Well, if you look at that equation, we said earlier that this angle, ABD, and also ABE were both half of the measure of angle ABC. Right? So I can use substitution and replace those. Okay, so then I can say by substitution, and then I'm just going to replace those, right? So then I would have, let me switch to a new color. So then I would have half measure of angle ABC plus, okay, this one I don't know yet, measure of angle EBD equals, and then I'm also substituting over here, half the measure of angle ABC. Okay. Now we can subtract 1/2 the measure of angle ABC from both sides. Okay, so I can say by the subtraction property of equality, this means that measure of angle EBD equals 0 degrees. Okay, well, what's the problem with that? So it's pretty clear from the diagram that it doesn't look like it's 0 degrees, but I need a more concrete reason than that. So it's a real technical one, and if you just go back, if you weren't sure where to go from here, you would probably go back and start looking for anything we know about angles and their measures, and hopefully you would eventually see the protractor postulate, and part of that says that the measure of an angle must be a unique positive number. So 0 is not positive, it's sort of a neutral number, neither positive nor negative, right? So we need to state the contradiction. Okay, so we would say, I'm going to continue this up top here, so I would say this contradicts the protractor postulate, which states that angles must have a unique positive number of degrees. Okay, and then since I know that there's a contradiction, there's a problem with this proof, but all of my statements were justified except for the very first one where I supposed that BE was also an angle bisector of ABC. Right? So then, okay, then I would want to point out that that is false. So I would say then BE is not an angle bisector of ABC. Okay, now am I done? So you might be wondering, well, okay, that shows that BE is not an angle bisector, but what if there's another one? You know, what if there's something in here that I didn't label in the diagram that may also be the angle bisector? All right, well, I didn't assume anything special about BE, I just chose some random letters and made this up, and I didn't even draw it anywhere in particular in this diagram. So the word for this is that the BE is arbitrary, meaning it doesn't really represent any particular angle bisector. It's sort of representative of all of them. It's kind of like using an X in algebra. All right. So sometimes we'll say, since BE is arbitrary, then we know that this conclusion is true. So I'm going to skip that part, but it's at least good to think about why we couldn't just have another angle bisector somewhere else in here that's not called BE. So basically we would end up with the same problem. Let's say I call one like BF or something. Then I could go through this exact same proof and I'd still get the same contradiction with having a 0 degree angle. Alright, so I'm going to end this by saying, therefore, since I reached that contradiction, okay, that BE is not an angle bisector of ABC, therefore BD is the only angle bisector for this angle. Is unique, and I'm just going to shortcut there since I've run out of space. All right, this is the end to an introduction to indirect proofs. So I think probably the next best thing to do would be to try some of these on your own, and then you can see if you're understanding this or if you have more questions about this technique.